All right, everybody, can we try and get seated, and we'll get started in just a moment here. All right, so while people are trickling in, I think we will get started. This will be the second session of our morning. We've got several really exciting talks coming up, starting with what I think is one of my favourite parts of the whole annual workshop, or at least it's a CEDAR tradition, and that's something we've sort of blended into the CEDAR GEM joint workshop, and that's our Distinguished Prize Lecture. This is something that CEDAR's done for as long as I can remember, and we invite a member of the community who has been active for more than 10 years and who's made ongoing significant contributions to our field to present a summary of their work on topics of their choice that they think will be of interest and relevance to our community. The speakers are selected by a nominating process. We call for nominations. Normally with just CEDAR, the steering committee would review the nominations. In this case, both CEDAR and GEM steering committees reviewed the nominations. We had a lot of really excellent nominations, and we were spoiled for choice. One of our requirements was to find a speaker whose work was of relevance to both CEDAR and GEM, and I think our selection process has found an excellent speaker for both of our communities. As I said, this is something that I think is one of the highlights of our meeting every year, is the Distinguished Lecturer. And so this year our Distinguished Lecturer is Phil Erickson from MIT Haystack, and I will ask Larissa to give an introduction to Phil.
Thank you. I could not think of a more deserving person to obtain a Distinguished Lecture Award at the CEDAR GEM meeting. And I wanted to say just a couple of words about our dear friend and colleague, Phil Erickson. Phil obtained his PhD from Cornell University a number of years ago. And right after obtaining his PhD, he came to work at the Haystack Observatory, where he remains since that time, and now in the position of director of the observatory. And as you see from the figures, on top with Nestor pointed at Hikamaka radar, and bottom you recognize well a receiver radar. Phil's early work was on something that we would call topside ionosphere. He was interested in light ion species and helium. And that was beginning of his research and involvement in in atmospheric region, which is really close to heart of both CEDAR community and GEM community. Who is actually Phil? Phil as a there are so many different aspects of who is Phil as a person. Phil is leading expert on remote sensor technology for multiple types of instrumentation, both ground-based and space-based. And one of the really unique qualities that Phil has possesses like unique combination of both technical skills but also space physics, really deep space physics, deep understanding of space physics involved in these multiple processes. As far as science itself, his area of research over the decades covered really broad area, starting from light ion behavior to mid-latitude ionosphere-thermosphere to suborbital physics to all the way to plasmaspheric dynamics, and covering all range of physics questions in heliophysics program. Besides all of that, besides being outstanding scientist, Phil is outstanding collaborator. And if I name just a few, I will miss 90% of number of collaborations and projects that he is involved in, all the way from working with developing systems on the ground and all the way to Van Allen probes. But besides all of that, Phil is really a compassionate and passionate leader for the community, who has been a leader at CEDAR and GEM for many, many years. With some of I wanted to highlight just a couple of really more recent activities that are really important for our communities. Phil was a co-chair for ITM panel for Decadal Survey 2024, which involves, as you understand, incredible amount of effort to have it happening. And he serves on National Cabinet Committee on radio frequency, which is an important part of work for community on advocating for science needs in spectrum, radio frequency spectrum. Besides all of that, I wanted to say a few words that Phil is absolutely outstanding mentor. Phil is enormously proud of enormously supportive of every early career postdoc, every student that comes through HESTEC Observatory door. And he's enormously proud and supportive, and really proud of all your accomplishments. And this is a picture just made literally just a few days ago with Phil and the current cohort of our students, IU students at HESTEC. So without a further delay, let me introduce dear friend and colleague, Dr. Phil Erickson.
Oh, yeah.
Advance the slides, hold it down, point it to
right.
there for a pointer. You've got about 45, 50.
Gotcha. Gracious. That was amazing. Thank you so much for the introduction. Larissa and I arrived at HESTEC just about the same time, within really a few months of one another, and she's one of my closest friends, but also one of my closest collaborators, and an EGU fellow to boot, so I should mention that. First of all, I have to thank the CEDAR and the GEM steering committees for this incredibly humbling and honoring recognition. I learned long ago, and in fact, this is something that we tell our students we have this REU program, we've been doing it since 1987, long before I got to HESTEC. And one of the things we do at the end of the program is we sit down with them and we say, you know, career advice, a little career advice. And one of the things we tell them is, understand yourself. You know, are you the kind of person that just needs to work on your own and just needs some resources, right? I am not that person. If you lock me in a room with a pencil, well, I'll come out with a pencil. Really, what I am is a person that collaborates with people, and that really is the place that I've been able to do the most benefit, I think. We're here in a community. We've heard about that this morning. This entire community has, in fact, the reason why I'm in this field really is sitting right here, and as we'll see over the years. And so I'm also very, very grateful to both these communities, and it's especially wonderful to have both CEDAR and GEM in the same place, because as I think I'll mention a little bit later, this field you need to understand everything about everything. And so the only way we're going to do that is coming together. So this is just one perspective on a few of the topics I think that Larissa has already mentioned a little bit. And I hope you find some inspiration in this, and I also hope you realize, especially the younger career people out there, boy, there's a lot left to do, and a lot of exciting capabilities that we have right now. So, and again, thanks to all my colleagues for support, inspiration, and material, which I have shamelessly stolen for most of this lecture. So I should start with just a little bit about my background, and some of you who know me have heard me talk about this before. I grew up in upstate New York in Schenectady, which is dominated by the General Electric Company, and in fact, their very, very famous research laboratory, which was one of the great industrial research laboratories of the 20th century, certainly, and is still doing pretty good work. And both my parents worked at the research laboratory in its sort of golden era, where literally the door would open and they'd say, here's some money, go do something useful, and the patent lawyers will be back. And then the door would close, and they'd come back next month, because things were just tumbling out of the sky, really. I mean, you know, the technology was just generating things left and right. You almost kind of stumbled across them. I had a neighbor 4 houses up who invented the artificial diamond. So, you know, it was just amazing kinds of research. So I was steeped in that environment from an early age. And in fact, so that's me down in the lower right-hand corner. That's Irving Langmuir's house, a few blocks from where I grew up. Langmuir was that Langmuir, the guy who liked plasma and the plasma frequency. He was the director of that laboratory. My parents passed him in the hallway occasionally, so I have 1 degree of separation to Langmuir. And there's a nice quote there from a nice thing, which says that the director said, "Would you like to play with something? Are you having any fun today?" I want to remind people that this is an environment that is evolving, but we'll get back to this. And he said, "I don't know what any good of this is to GE, but I'm having fun." And he said, "That's not your worry, that's mine." And he went back to doing stuff. On the left-hand side there, by the way, if you don't realize that, that is Langmuir, and the guy next to him is Kurt Vonnegut's brother, Bernard. And the guy leaning in is Vincent Schaefer, and they're basically making it snow. That was just after World War II when the seeding of clouds was a thing for weather control. It didn't work out, but my point was that if you've ever read some Kurt Vonnegut novels about Ice 9, that's where that came from, actually. Anyways, so this is the environment I kind of grew up in, and it turns out that my family also was an influence in me getting involved in radio wave stuff. I put this in for Dave Heisel. That's a vacuum tube receiver which was sitting in the upper floor of one of my relatives' houses in upstate New York. And with that and a tiny little cheap frequency standard, I listened to all of these other shortwave signals, and that's kind of what got me interested in radio as a mysterious thing that had propagated over directions. The bottom finger, I have the receiver in my office. I need to restore it. I will also just point out in passing that it's a little ironic that one of the things I heard was the Voice of America, if any of you have been keeping up with the news about the Voice of America, and I hope that that is something that will be corrected pretty soon. So with that background, I ended up at Cornell, and people who are, pillars of our field, I work with Don Farley and work with Mike Kelly, and work with Wes Swartz. And as Larissa mentioned, I was working with both Jicamarca and Arecibo as incoherent scatter radars, which I'll talk about in a minute. And the idea was to look at things like helium and hydrogen in the top side, which is still an interesting topic, and one that has still a lot to be done. The bottom right-hand corner is, in fact, the helium density is a function of time over an Arecibo experiment of about more than a day. That's winter time when the neutral helium bulge drops. So there's some interesting chemistry up there. So gradually I got more and more interested in this interesting technique of large aperture high power radar, or incoherent scatter radar. And then I ended up at Haystack. By the way, I want to acknowledge John Holt, who we just lost John Holt earlier this year. John was a pioneer in this community, and many of you know him, and if you didn't, it turns out that John invented a lot of stuff that we are still using in CEDAR today. My very close colleague and friend, John Foster, who is, we wrote a paper together just last year, so John is still doing quite well. And then the late Michael Bonsanto, who we have a lecture for every year at Haystack, a really tireless CEDAR member and organizer of countless storm workshops. That's a partial picture of the Haystack group. We couldn't find everybody at the time it was taken. And the top part is the Haystack Observatory Complex in Western Massachusetts, which is actually shared between MIT Lincoln Laboratory, which does Department of Defense work with large radars, and Haystack Observatory, which I'm incredibly honored to be the director of as of last year. And then the bottom one is what the CEDAR community knows quite well, the Millstone Hill Incoherent Scatter Radar, which is in Westford, and you can see the truck for scale. Those are pretty large systems. But the idea here is that you also have fun when you're doing this. The upper left-hand corner is a person keeping an eye on theorists. You have to be careful with the theorists. They might get at the equipment. The bottom one was an amazing trip to Irkutsk, Siberia. It would be nice to be able to collaborate with our FSU colleagues as much as we did back in the late 90s. Students up in the Arecibo control room, in the middle of the 18,432 dipoles that make the Jicamarca array in Peru. And then the top is actually a one-week guest lecture that I was doing for a few years up in Kiruna for the Erasmus Space Masters program. And those are cantennas. So that's a little tiny radar where you can do Doppler and ranging with literally 2 coffee cans. We used to get the students to actually go and try to find a coffee can, and then we would use it for the antennas. Unfortunately, they don't make a lot of coffee cans in Europe that are metal. And it turns out one time they found a biscotti tin. So we actually did radar with a biscotti tin. That was fun. So we have a lot of adventures in this field, right? You go a lot of different places. It's also, you know, I set a serious tone at Haystack. The right-hand one is something I keep on my wall just to remind myself not to take myself seriously. And the left-hand one was a picture that went very wrong at Haystack when we were trying to get a group picture for one of the workshops. And poor Anthea couldn't see into the sun, and I thought this was really great. So one of the things you tend to do is you have to have a sense of humor in this field, and I hope I managed that. So Haystack is an interesting place in that even beyond the things that we normally do at CEDAR and GEM here, having to do with upper atmospheric physics, we have a lot of science and technical disciplines. We do radio astronomy, we do geodesy, which is Earth orientation and rotation. We're trying to get CubeSat programs going. We do a lot of polar science, cryosphere work. And the point here is that it's really science and technology welded together. If you have people who understand not only what the technology is, but what the science applications are, you can do amazing things. And I think that is something that this community is also, as you'll see later, beginning to gather to itself, is understanding both of those and having them work in tandem. It's an incredibly powerful thing. My message here is that this occurs not only in our field, but in these other disparate fields to great effect. So I'll concentrate on the Millstone Hill Geospace facility for a moment, and I should mention that Larissa, who graciously introduced me, is now the lead PI for the Millstone system, as well as being the leader of the Geospace research group, as I've taken on some other responsibilities, although we keep talking. There are three really pillars of this NSF-sponsored facility. There's the Millstone Hill ISR, which I'll talk about in a minute, and then there's a very popular GNSS total electron content, and then the Madrigal distributed database system. And I'll go into a little bit of each of these in a little bit. But my point is that this has been a pretty good engine, I think, for the work that I've been privileged to do in this community. If you go to flea markets, you sometimes find books that were written for middle school students in 1958, and if you're lucky, you can find yourself in it. So that is a book that you can see there with 16 pages of photographs that happens to describe science when, look at the date, this is, a few months after Sputnik was launched. And it turns out that we were already doing things at the Haystack complex then, and it turns out that the complex, which was designed to do ballistic missile early warning prototyping, that's at a power aperture product that's big enough that you can actually do ionospheric science if you are keeping up with the technology and you know that something at that level is also capable of doing this really, really challenging measurement. So this is something called, we like to call it incoherent scatter. That's now you could call it collective Thomson scatter, and you can talk to some of us about which phrase we like to use, but the point is that it's a very different thing than 95% of the radar community that you could go to an engineering college to talk to, because it's incoherent. You're scattering off a random process. It's very weak because you're actually moving around electrons, electrostatically restrained by ions. But if you have a big enough system, like you showed up in the 1950s for other geopolitical reasons, you can do amazing things with this. And so that's what I've really spent a good amount of my career doing. As we tell people in this one-week crazy crash course in incoherent scatter radar techniques that we run every year, we're doing another one in July. This is basically, you've got a box of thermal electrons, and you're picking out, when somebody gave you a radar frequency, those targets that are spaced by the Bragg wavelength, so lambda over 2. And then you're basically looking at the electron density statistical distribution. And there's this lovely first principles plasma theory that then allows you to invert that and get all sorts of parameters on the thermal plasma. And it's really weak, so you can do it as a function of altitude. 200 kilometers doesn't throw enough energy away to worry about 300 kilometers. So if you do these things, and you apply really good plasma theory, which was developing in the late 1950s to the point where there were actually multiple sort of approaches that almost yielded the same thing. You get electrons which gather around, you get essentially, well, let's start with, you get big, heavy, pokey ions which gather around electron clouds around them. And then you also get electrons themselves. And if you combine those two, you can make circuit analogies, you can make, again, first principles plasma analogies. The scattering you get comes from these electrons because the mass is light, but their fluctuations, because they're hanging around the ions, contain a lot of ion information as well. So you can turn this into a very nice remote diagnostic. You can start with the ion acoustic mode, which is literally acoustic vibrations in the plasma. You know, I'm using pressure variations to talk to you. In this case, the electrostatic field is the restoring force, but it's really an acoustic expression, so you can see a square root of a temperature over a mass there. And so if you do that, you can actually watch those spectra, which is on the right-hand side, change shape as a function of altitude. And what you've done now is you've done a full altitude profile in the direction that the instrument is looking. And you can do this statistically, maybe, depending on the system, every 30 seconds, every 45 seconds. And so you can build up an enormous amount of information about not only the electrons, but the ions. Yes, there are ambiguities, but we've learned how to deal with a good number of them. And so on the left-hand side there, you can start deriving the bread and butter: electron density, plasma temperature, line of sight velocity, ion composition in some cases, and then you can get more exotic. If you can make the electrons and the ions flow in different directions. You can get field-aligned currents. You can look at photoelectron spectra. You can look at unequal ion temperatures. Well, Arecibo could do that. Someday we'll have another instrument like that. You can look at non-Maxwellian plasmas. You can start warping the theory. It's just an incredibly powerful technique. And so you match the theory with the observations. You use inverse theory, turn the crank backwards, and you get things like on the lower right-hand side, which is what for example, the person who is studying physics would like to know. If you go back, I like history, right? If you go back to the history, this was originally started again by John Evans. John Evans, who was a group leader at Lincoln Laboratory. There was this 84-foot tracking radar, which was not built to do the ionosphere. He borrowed it nights and weekends because he knew that this thing with the developing theory, and he made plots like that one, which I copied out of his notebook, which was done using a bunch of analog filter banks, and you get this very famous double-humped spectrum. And there's a paper from the early 1960s about this. So, going all the way back decades, this was recognized as being a very important thing, and of course that's now a real pillar of the Geospace Facilities program at Haystack. And if you're really lucky, you get to talk to John, who visited us 3 years ago. That's John down at the bottom in the center, and you get to hear from John about what that was like, and to realize that he was still interested in a lot of the problems that he left behind in the mid-'80s when he went to ComSat. And so that's another thing in this field, that you can synthesize knowledge across generations. And I think that's one of the wonderful things about this community, is that when I come back to this meeting, I see familiar faces as well as new ones. And so there are friends that I know, and there are friends I have not met, but there are also colleagues of the same sort of ilk. So we're really lucky to have people like John still around. Heard from him about 6 months ago. He's doing well. And then you get to my friend Langmuir, who I talked about earlier, having this strange family connection to indirectly. There you're looking at the actual vibrations of the electrons. And so it's a very weak scatter. You're inside the Debye sphere, if anybody knows about plasma theory. It's typically daytime only. You kind of need enhanced photoelectron fluxes to get that really weak thing above. But it's a measurement of a frequency, not an area. So to first order, if you get those peaks, you can figure out exactly what the plasma frequency is to within a fraction of a percent. So if you do that, and you zoom your sort of spectrum out, the ion acoustic line I showed you before is that little thin line in the middle. And then those little weak lines right there are the Langmuir lines or the plasma lines, and you can determine the electron density. Arecibo made full profiles of this. We're trying to find some time to do that at Millstone. You can see the SNR, it's really weak. But the point is that you also have this available. So you can get altitude resolved plasma state parameters. This is a little small, but you can get electron density, you can get ion temperature, you can get electron temperature, line of sight velocity. You can watch things change, for example, as sunrise happens. So all of this is flying out of this technique, or if you have a steerable antenna like we do, and you steer it toward the deck, you can see in the inner plasmasphere, into the plasmasphere boundary layer, off into sort of the trough region, and then into high latitude convection. And you start really measuring not only space weather, but you also measure a lot of other fundamental things. I want to point out that 3 or 4 years ago, there was a strategic vision for ISR workshop report, which I highly recommend that you take a look at, because it turns out that, again, as John Evans knew way back in 1960, if you have something at this power aperture product, you can do all of those things that we see on the right-hand side there. You can read them, especially if you have multi-static radar architectures now, not just single antenna, which receives and transmits. These are all cross-cutting, and they fit very well into the CEDAR and GEM cross-cutting themes that are the subject of GEM focus groups and also of the CEDAR sort of thrusts. And my friend Juha Virinen, for example, borrows the radar and turns it to the moon and makes a nice lunar map with it. And I was apologizing to Juha before because this is not the best nice focused image. But the point is, these are multiple systems. And by the way, if you turn off the transmitter on these systems, it's a radio astronomy device. So this is what we can do now. The technique may be decades old, but the portfolio just keeps opening and opening and opening. So I want to advertise the fact that there is an effort going on to try to generate a textbook about this, and you can see there, it's e-sported, and you can see some of the people who are leading chapters, and then the community will be helping to contribute to this. Suitable for master's and PhD students and above, and if we're really lucky, we get this out by 2028. And we want to have computer code like Python notebooks with it. And for example, reference spectra, if this is the plasma parameters you put in, this is what the spectrum should look like, so that the field, has a reference later if someone wants to reproduce things. You can't read the chapter outline, but we've already gotten to a chapter outline. This is led by people like Koki Chow and Lisa Baddeley and Gareth Perry. And the nice thing is that we're going to actually go through parallel theory chapters, rather than, if someone was really interested, going all the way back to the original papers with all sorts of different variables and trying to figure out what's going on there. The idea is to include full theoretical derivations along with everything else. And so it is not the single only book that has been written about ISR, but we hope that it's going to be pretty comprehensive. So look for that. So let's add more things. You might know that if TEC maps are very, very popular. This is differential delay on the GNSS transmissions, and that's the whole reason why your phone works to navigate anyways, is because you're using two different frequencies, and the ionospheric delay causes a differential delay. And Anthea Koster, when she came to Haystack, really brought this technique with her, and now we generate, through the Millstone Hills Geospace facility, these extremely rich pictures of cold plasma in the ionosphere, especially over the continental US, where there's like 2,500 or 3,000 receivers, all putting up their data for free. Like you get 500,000 line of sight values in 5 minutes. So this is like, red meat to a assimilative type of, or an empirical type of modeler, and I'll talk about that in a little bit. So let's add, right, we've taken that very, very nice technique, let's add more. Let's add more. Let's put the data all in a place where hopefully it can be gotten to easily. John Holt created this originally in 1980 as just a way for internal people at Haystack to get to incoherent scatter radar, and it has grown far beyond those boundaries. And Kay Cariglia is now assisting Bill Rideout, and there's a transition from Bill Rideout to Kay, and is now pushing this forward into the future. And you can look at your favorite instrument in there. One other thing that this also highlights is that no one instrument has the full picture on what's going on in the upper atmosphere. They all have pieces of it. You have to synthesize. You have to put everything together, and then the insight starts coming. Larissa mentioned HAMSci. This is another effort led by Nathaniel Frizzell very energetically, and he's talked about this in other motivations, to not only do this with our normal professional networks, but to do citizen science with this. And you take a bunch of guided sort of individuals that are very technically eager, and you end up realizing that for their own hobby purposes, they have databases that have billions of records in them. If you get those in, you align them on good coordinates. Some of it's available in real time, by the way. You can do wonderful combined measurements like this one, where you can see super darn on there, differential TEC, and then also these crowdsourced amateur radio operations. And there's a very nice paper that Nathaniel put out a couple of years ago looking at large-scale traveling ionospheric disturbances, not in these particular contacts, and actually tracing the bottom side of the contacts that people were making in terms of sort of forward skip distance, and then figuring out interesting things about LSTIDs in ways that were really not possible before. So observational synthesis, right, leads to insights. I do want to mention this. You even can tell your father, who at the time was 88, he's since passed on, to get out his shortwave receiver when the August 2017 eclipse happened and just listen to shortwave signals and just tell me, Dad, how bright they are. It turns out there's a good amount of physics in that. You'll notice that there's some responses that actually are not aligned perfectly with the local passage of the shadow. So this is what citizen science can do for you if you plug it in, and Nathaniel's really leading the way here. So it's been a privilege to be involved with some of that. Let's keep on adding more. There's this MIMO meteor radar technique that Koki Chow at IAP has pioneered, and that Ryan Volz at Haystack is also working on a mid-latitude system near our particular system. Divergence, vorticity, momentum flux, mesoscale structure. If you read a lot of the decadal, you will see the word mesoscale appear a lot. It's really one of the undiscovered frontiers. All of this is more commercially available technology that's really dropping in price. You can add to that low-cost ionosphere networks. That's what John Swoboda is working on, which are fully vector capable, so you can do angle of arrival stuff. And let's add that to the picture. And then let's add it from orbit. Here's GDC. Thank you to Bea for giving me this slide. Let's make sure we put a 6-satellite mission up in different longitude planes so we can start to unravel MLT dependencies on things like, for example, a storm-enhanced density plume, which is a famous mid-latitude feature that we've been working on for a while that you can see in the background there. It's interdisciplinary, right? But all that other stuff I showed you, which, and I'm admittedly a ground-based person, so I'm a little biased, is also interdisciplinary. Or dynamic. Dynamic is going to start to really hack at 100 to 300 kilometers. This is really hard stuff. This is VLEO. It's hard to put spacecraft there too much of the time, but this also has the electrodynamics. So you take the GDC and then you combine it with the electrodynamics, and now, again, you're doing this interdisciplinary, multifaceted, multivariable kind of study. Or your EMMA, and you put 27 magnetometers, 27 rheometers, RGB, full color ASIs now, spectrographs. Look at the map. You do that in coordination with GDC, and you do that from the ground. Again, you can see how much data is beginning to pile up now. Space is still sparsely sampled, and we're not the meteorologists here, but it's getting better. So all to me, that's exciting. Now, what do you do with it? So I think the last part I'd like to talk about a little bit is, I want to just shortly divert. This is the Haystack history wall. If you come to visit Haystack, this is sort of our history from the 1950s to the present. Every single thing in this wall is a consistent reimagining or synthesis of capabilities that were already there that just got changed. For example, I talked about ISR before. Well, if you're an astronomer, you can make the first image of the black hole, for example. What do you have to do? You have to combine distant radio antennas with good clocks from all sorts of different places, and the result literally does not exist until those pieces of data come together in an analysis package. We like to say to people, the black hole image, it's in the correlator right there. It is not at the telescopes. So you can do literally one of the most challenging radio images that humanity has ever made about the black hole. Why am I bringing this up? Because of that. You have to do this globally. There were 300 people involved from 59 institutes from 18 countries. Without this international open collaboration, that result would not exist. There are analogies to this field. We collaborate internationally. We need to continue to do that. So there are very nice parallels of what comes out from these other communities with this sort of multi-messenger technique. So how do you do that? I just talked about all this data, so how do you get a floor on beginning to assimilate it? Well, you do things like my colleague Urcha Ah with TIDAS, which is essentially a 3D data assimilation. You try to put everything in the box with all of its advantages and disadvantages. TEC, cosmic radio occultation TEC. When we have the radar, put that in. We have downward-looking TEC from the Jason satellites. You try to assimilate all that together and get a better empirical picture. And then you start attacking, for example, just at mid-latitude and subaurals, all of those things I pulled out from that facilities workshop report that I mentioned before that a few of us had gotten together to do. This is incredibly rich, and it touches every piece of both CEDAR and GEM, the reason that we're all here. There's just one example of cold plasma life cycle in the Geospace system, but you can look at SAPs, you can look at subauroral ion drifts, you can look at medium-scale TIDs, log-scale TIDs, interhemispheric asymmetries, a favorite subject of AGU sessions, mesoscales, I mentioned mesoscales before, and the very important plasmasphere boundary layer, which is where in mid-latitude and subauroral is where a lot of the action is now. And you synthesize, and John Foster and I like to call it the Geospace plume. Other people have different things. But the point is, the life cycle of cold plasma through the entire system has a fundamental and profound effect on many, many things, from wave particle processes to literally dynamics of the whole inner magnetosphere. But you have to look at it from these different views, get it in different coordinates, and realize that you're looking at a lot of the same processes and that it's a system. So I bugged Gianluca Delzano to give me a little piece of the updated cold plasma questionnaire. Some of you may have seen that in the GEM community. The idea was, where were we 5 to 10 years ago? What have we learned in the past 5 to 10 years? And where are the remaining gaps? And you heard this morning that particular focus group is completing its 6-year run. There's the cold plasma focus group sessions. I just will point out there's some words there. The complete dynamics of cold plasma are still a long way from being understood. Until you understand them, you can't understand the MI system. How the structuring works and what controls it is still a mystery. And a lot of nonlinear wave-wave and wave-particle interactions are pretty much completely unexplored. We need to explore them with this knowledge, and then there are about 5 or 6 other things I don't even have time to mention here. So go to the sessions if you can manage to make it over there. But Slava Merkin gave me this, and I think it's nice. It's a complex system, right? It's strongly coupled. You have to treat the whole thing as a whole. It's the tyranny of scales. Small things, because of magnetic mapping, map out to larger things, and some scales are in the inner magnetosphere, and there's some are on the ionosphere, some are transmitted back and forth, some are not. The physics is still incomplete, as I don't have time to talk about, but we're also missing parameterizations. And the point is, we even have trouble with the initial and boundary conditions, because again, this is a hard system. That's why space weather is hard. It's really tough to do this from first principles. That's why I think the really exciting part about all of these different distributed heterogeneous sort of measurements is now coming to play to actually meet the MAGE environment, which has got a ton of different things. Look at what we've got there. This covers all of CEDAR and GEM. We've got the ring current. We've got the transition region. We've got, the global electric field picture. We've got the polar wind coming out of the high latitude regions. We've got WACM-X that's getting the physics and chemistry of the coupled thermosphere-ionosphere system, even down to the mesosphere. And then we've got SAMI-3 looking at cold electron density sort of structuring. There's a lot of exciting developments there. Go to the workshop on Thursday at 10 to 12 to learn a lot more about them. But again, and there's a website down there, by the way, if you want it, but I find all of that very, very exciting. This is the assimilative and first principles modeling coming together with all of these other heterogeneous data sources. This is really exciting. We're at the cusp of doing amazing things here, I think. And it's even buried in the CEDAR New Dimension that Laura Waldrop, who was the engine of progress with me on the ITM decadal survey. You go back to 2011, and it's in there. It's a system science perspective to study things, where you really do need to put things on a common table and figure out how you can get the information flowing back and forth. We think the overarching goal of science in the next stage is a systems perspective, processes that cross regions, processes that cross scales, relative significance. Maybe everything's operating, but are at certain times, is this more important than that? And then the origin of persistent changes in the ITM state, punctuated equilibrium, things that slowly evolve until they suddenly jump state. Impulsive events are, in fact, opportunities to study complexity. Some of you recognize the Hunga Tonga eruption, which shot an enormous chunk of water vapor high enough in the atmosphere that it started affecting the interhemispheric circulation cells, large atmospheric chemistry changes, and then other things like volcano explosions or even fertilizer plant explosions. All of this is a system that needs to be understood as a whole. Evolution of geospace, period, we found from a lot of the white papers we read, is still poorly understood. The evolution of complex dynamical systems is not a linear one. If you study that theory, you find that out right away. You need physics-based modeling constrained by whatever poor but large numbers of views that you have of the system, which is what I started out talking about. There are notional concepts in the ITM survey, which, again, we'll have a workshop literally after lunch today that you can come and we'll kind of provide an overview of the ITM panel and then have a community discussion about some general things that we think are coming out of there and see if we can start, again, more efficiently welding these things together. It's a challenge, but it's an exciting one. What I want to end with is, we've heard the word community a lot today. This is, of course, existential. It's essential to our future as geospace scientists, and heliophysics, in fact, is fundamental to society. So this is a photograph that I'm in, somewhere there. I think on the right-hand side, maybe in the middle row. This was taken up at the Mesa when CEDAR was small enough that we were at the NCAR Mesa in 1990. The other thing I have there is the very first CEDAR report from 1986. This was before I was still an undergraduate. I hadn't even started graduate school yet, but this was the beginnings of a catalog, and this is where CEDAR grew out of. And we're still here, nearly 40 years later, still finding interesting problems. It came out of the community. That, in fact, quite a number of those people hung around in the community because they're clever people, but they found something interesting. They had other options, but they hung around, like me. This is our future, folks. So you can see whether it's people at Haystack presenting posters at the end of their 10-week session where they completely astound you with going from knowing nothing about the field to preparing an AGU presentation like Cole Tamburi down there in the lower left-hand corner, or preparing a very nice AI machine learning model like Matteo Serrano down in the lower right-hand corner. You've got Claire Gasquet up there, who is now a full scientist at Berkeley. This is our future. This is what this community can keep going if we work together. Despite all the headwinds, despite everything that is happening right now, I want to leave, this gives me hope. These pictures give me hope. So, Larissa showed this picture. This is our 2025 RU class at Haystack, so that's radio astronomy and geodesy, but it's also ionospheric physics. And down in the bottom right-hand corner there is people working with a particular, for example, open radar workshop where we try to show people some tools. You even have people show up from the MIT Radio Society and say, hey, would you give an introduction to radio? Which I didn't know what I was doing, and it turns out it's on YouTube, so you can watch me do that. Different ways of gathering and keeping a community. And I know this will be talked about on Friday, but there are also very active efforts, even at DC. There's a tear sheet on the left-hand side, which was left behind in a lot of staffers' offices, about why heliophysics. Not just about studying the sun, why it matters to society. Inevitably, this is a spacefaring society. We have to understand the environment we're in. There is no choice. So the photograph there is Robin Milan and Amy Kesey and Kevin Genestri out in front of Maggie Hassan's office in New Hampshire meeting with staffers. There's also a scientific society letter down there in the bottom, and I'm sure that, again, Ian and other people will be talking about that in the Friday town hall, so please make sure you come to that. This is the way we keep our community together. But I'm hoping that you can remember that all of the rest of the things I talked about in these very diverse areas are places for hope. It is places where science is really exciting, and it's a place where I think we can make a difference for literally understanding our planet and its home in the solar system. Here's an example, and yes, it's a bit exaggerated because, of course, on the left-hand side, the dots, the satellites aren't that big, right, compared to the rest of the Earth, but this is the societal challenge of low Earth orbit. I can tell you how much impact this makes with people who visit the observatory, and I show them this. Or I show them the bottom graph that says there were 529 Starlinks in 2020, and there are now 8,223. They are licensed for 12,000. They have applied for 45,000. They are one of a dozen networks that are now applying to go to this density. You have to understand the space environment these are in. We can't just have a throwaway society that says, well, you know, we lose 40 of them because we have an event, we'll just launch more. That's not a terribly good way to go about things. This community is the place that can help that. And this really does seem to resonate with the general public when I show this. They had no idea. So what I want to just end with is, again, I think we're just getting started with this exciting system scale understanding. It takes every single tool we have, and it takes this community talking to each other and working together to unlock the insight. Community is fundamental, and pendulums swing, and eventually the pendulum swings back to the center. I'm hopeful and I'm convinced that we'll persevere together as we're going to be doing the rest of this week. Again, it's a very great honor to give this lecture. I appreciate your attention, and I'm looking forward to doing science the rest of the week.
Well, thanks, Phil. That was fantastic. And I think that was a really powerful demonstration of why we actually have a distinguished lecture. You know, inviting someone up here who's had a long career perspective can sort of help us bring together and see how our community actually works together and how all the things we do come together. I was thinking, you know, if I had some sort of real-time software that could create a word cloud from what we just heard, some of the words that would appear prominently in that would be synthesis and system and community. And those are all so important to us right now. And in particular, I think what Phil showed us is that the problems that we need to tackle need all of us to contribute. So you can have a single investigator at some small institution running one instrument, but that contributes to this larger picture that Phil is talking about, and we all need to contribute to that. And clearly, from his end, you know, society needs us to be doing that. So that's really great. And so that's exactly why we have these distinguished lectures, so that, you know, we can get that sort of perspective. I think we do have some time for questions, and we have some mic runners. So if there are questions out there for Phil.
There's someone. I can't see who it is because of the lights, but it's somebody in the back.
Okay, I'll just talk then. I was told to be quiet until someone else spoke, but no one else is speaking. So, Phil, thank you. That was fantastic. One thing that really shined bright to me and is fantastic about Millstone and Haystack is the commitment to education. And particularly in our field, we've got a lot of research institutes that are not as closely linked to universities. And over the years, Haystack has remained tremendously connected to that educational mission. And so I'm curious if that was intentional, or is that something that just came along the way, and how you've continued that theme?
Yeah, thanks, Brian. So none of us at Haystack are faculty members. We are all sponsored research, okay? So we are, you know, supported fully by grants of one form or another. And what we realized, I think a while ago, so the intention, I think, Brian, was that, you know, it's harder for an individual university department to field the kinds of systems that we're talking about, or to do the routine synthesis of 6,000 receivers from everywhere else. But you don't have to duplicate effort. And so the idea is, again, it's putting together. If you can put together the researchers and the graduate students with these kind of tools, which, for example, are supported by NSF as a Geospace facility, then I think you get the best of both. And there's one other thing I will mention that is one reason why we've been doing a good amount of this, is that you know, there's a debate about the community about if all instruments are remote, does anybody actually have to go to a site, right? And it turns out that if you talk to people at least once in their career, being in the physical presence of instruments like that, there are things intuitively that start to connect in the back of your mind. We are easily accessible. So that's another way that I think that regionally and also even more generally, we're able to sort of help, even though we are not in the direct business, for example, of generating graduate students like you are. Oh, yeah.
Yeah. So a lot of us throw around the term mesoscale, and you mentioned it a couple times. What does mesoscale mean to you?
Okay. Boy, yeah, that's a good one. Anyways, to me, again, coming from a MI coupling, coming from an electrodynamic background, I think to me it is things that are sub-degree, so degree is like 100 kilometers. So you're in the tens of kilometers to the kilometers and even below. If you're going below kilometers, now you're getting into the the domain of irregularities and those kind of processes. But it's those other mesoscale structures, when I say mesoscale, at the tens of kilometers and maybe down to a few kilometers, which you could see, I went by it very fast, but in the mesospheric, in the meteor wind data, you have all of these whorls, vorticity, and other kind of structure in the neutral atmosphere, which just is not in a lot of things like the HWM or other kind of models. So I think it's not only finding out what those scales are, but also finding out what is important for which physical processes. That is another thing that I think you'll see in the decadal, especially in the panel report that we worked on. That is the place where I think the techniques can kind of come together. And I know things are going on at mesoscales that we're just not either representing right in models or even observing yet. So that's why I think that's exciting for our next phase.
Hi there, Phil. So something that really resonated with me was your discussion of synthesis and needing to combine the data from several instruments and several different perspectives. And I noticed that you also highlighted the Madrigal database with the collection of data from so many of these different sources. There's also, for the GEM community looking further out, there's also the CEDAR web that NASA hosts. Yep. However, both of these, I'm actually not entirely certain how Madrigal gets funded and maintained, but I know that, for example, CEDAR web, it's entirely funded by NASA funding, which we've all heard what's potentially coming up in the future for that. We've also seen what happens when, for example, NOAA starts no longer being able to host their database of some of the space weather data they've been collecting. First of all, how much of a risk do you see to the maintenance or potential loss of these kinds of databases? And secondly, what do you imagine, or what ideas do you have to be able to retain these kinds of databases, not just for the data that already exists, but also for future missions, future instruments, and future data sources that will be needed to continue this kind of synthesis?
Sure. No, thanks very much. Madrigal, in fact, is funded by NSF. It's one of the things that forms our Geospace facility. So, NSF is doing that. NASA has for a long time been doing CDA web, and then has been funding some software interfaces like, PyDAS and other kinds of things to access them. I think that one of the things that we've been talking about is, how do you make those arguments to a non-federal, for example, sponsor, right? How do you then say that, literally society, I showed you that picture of things going into LEO. Society needs to maintain this information, and I don't think that we should, so we're trying to get creative about it, and I don't have anything specific to say in general, but I think that it's kind of like your portfolio, diversifying in more than one source is probably the way we want to go forward. I will say also that making that case to other people of maintaining these databases is also going to be facilitated if we also work on ways to share metadata between the particular facilities for discovery. In this voxel, there's a ground-based measurement. At the same time, there's an in-situ measurement. This is not an easy problem, but if you look at the community of transforming data access, I think that's also going to help us make the arguments to these other sponsors that this kind of information is very rich and that it isn't just real-time. Many people operate in a real-time environment where 10 minutes later, it's dropped on the floor. We have a unique thing in that we do long-term trend studies that go over decades. We have people who, are digitizing, ionograms from the 1970s and getting them into a database with uncertainties. By the way, I didn't even talk about quantified uncertainties. Right? Space weather quantification of uncertainties. That's a big, big thing, folks. For those of you earlier career, please put error bars on your plots. I know how tempting it is not to. But in any case, I think that it's being creative, and I think it's also seeing how we can solidify the arguments that we can then make to not only foundations, private sources, but also to our elected officials, frankly. So yeah, this is something that I think that we're working on as a field, and it's going to be part of our future, completely. Hope that helps.
We maybe have time for one more question.
There is a question in Slido by Jason there. The question is, why is it insufficient to have frequency dispersion information for finite bandwidth L1 or L2 as opposed to two distinct frequencies to determine DTEC?
Okay, wow. We went way down the technical rabbit hole there. I'll just say very briefly, and then Jason, you can find me later, that the differential delay sort of setup of TEC really, again, was done for navigation to say that the one thing that the differential delay, the ionospheric correction drops out of it, because it's the one thing that from physics you can understand. If you understand the two frequencies, you can relate the integral of electron density to that particular differential delay. It's not the only way to do it. But it is the way that, for the way that the navigation system was set up, is the most practical and has been adopted. You might know that GPS has multiple frequencies now, and if you combine more than one frequency, which I haven't seen too many people doing, you can perhaps increase you can even make the uncertainty on the absolute TEC even better. I'll just end by saying that it is a matter of working with what you have. This community did not launch all of the GPS satellites, nor does it maintain the clocks. But it can very well use this product that literally is a headache for the people who are doing navigation, and just, they don't want it. We'll take it.
So let's thank our speaker again. Don't go away. Don't go away. No, stay there. So I can't let Phil leave just yet. I will say I was very impressed with his answer to a rather deep dive question there. That was nice to see. So, as is the tradition, the distinguished speaker invitation is always regarded as a significant honour in the CEDAR community, and so we have a certificate of appreciation here framed that we would like to present to Phil to thank him for giving us this lecture. And I think this time we're presenting it on behalf not just of CEDAR, but CEDAR and GEM. So.
Which means a lot.
Yeah, thank you, Phil.
Thanks, Mark. Yeah. Really, really appreciate it.
Yeah, no, that was great.
Thanks.
Thank you. All right, it's time to move on. So I think our next presentation is from Alison Janes, and she will be speaking to us on outcomes from the decadal survey relating to effective public outreach. So thank you, Alison. I think you have 20 minutes or something.
Okay, thanks, Mark. All right, so I was asked to speak about the outreach that we put into the decadal survey and some of the findings and recommendations that we had in there. So that's what I'm going to do. But I wanted to start with a question first. So how many of y'all are sitting in your seats today because you were exposed to some sort of outreach in your early formative years? Raise your hand. Okay, so that could have been, YouTube videos, or watching Carl Sagan's Cosmos, or seeing someone at when you went to a museum talking about astrophysics, which, let's face it, is normally how space science gets conveyed. But in general, I think a lot of us have had some exposure early on, right, that kind of got our minds thinking about being curious about those types of questions and topics. So I'm going to talk today about that kind of outreach. But I know a lot of people are thinking, like, why does that even matter? our funding is in jeopardy. We're talking about, making decisions about our careers right now, hard decisions. So why are we even talking about outreach? And I wanted to say that honestly, part of the reason that we're in the place that we're in is because of that lack of outreach, right? And not being able to communicate to the general public how important our research is. Not being able to communicate to legislators how important our research is. Phil had mentioned the congressional visit. A lot of us in this room were on Capitol Hill last week talking to our reps and our senators, and many of them have kind of no idea about the Sun-Earth system and how that affects their states' economies, the farming industry, GPS and connectivity. They just don't know. And so this is not to make everyone in this room feel guilty, because this is not your job, but part of the reason they don't know is because our field doesn't communicate effectively to the general public at large. Okay, so let me tell you some of the things that we talked about in the decadal survey. And we kind of went through a number of topics about where outreach opportunities are possible. That includes informal education to the general public, to STEM students, citizen scientists, cultural groups and cohort groups, and other career paths that aren't already in the physics and astronomy world. So I also want to ask another question, is how many people in this room have been involved in some kind of outreach as shown on the screen? Amazing. Okay, yeah, excellent. That makes me super happy and excited. This type of work takes time, but let me give you a different perspective on that. It doesn't so much take time away from my research. That is one way to look at it. But rather than think of it that way, I actually feel like it gives me more energy to do my research and be excited about my research. So those of you who've been involved in outreach know how incredibly cool it feels to be in that room, talking to people, making connections to people, to students, to the public. And that actually kind of fills me up and gives me the resilience and the energy to go and do better science. So in the end, it's like a time-saving technique rather than a time sink. That's just my perspective, but I'm just going to put it out there for you. So I'm going to go through these categories and talk about what we found and what we reported on in the decadal survey, chapter 4. But I wanted to also recognize that there's a lot of stuff going on that wasn't in our report that we didn't comment on. And those are things like HAMSci that Phil mentioned just a few minutes ago. There's the Arctics group, citizen science group, an ISTE team that is developing a Aurora Watcher's Handbook for citizen scientists. There's our own Vincent Ledvina in the room somewhere, the Aurora guy, who just on his own makes outreach a different world for our field. And then Fran Bagenal, who I had the pleasure of working on this chapter with very closely. She's just a powerhouse, right? She goes and does everything and talks to everyone and probably is responsible for a good fraction of the people that are in our field at all. Okay, so let me talk about the formal education settings first, because this one's pretty fraught, actually. So we had a finding in the decadal survey that said that solar and space physics science has not been fully incorporated into US education at either the K through 12 level or the undergraduate level, in the same way that astronomy, astrophysics, earth sciences, and planetary sciences have been. And we see the impact of that in the ways in which people think of us as astrophysicists or call us astrophysicists, right? And then also the ways in which people don't understand how that Sun-Earth connection is having a role in their lives and in our technology and just in the things they see in the sky, right? So we haven't done a good enough job as these other fields of incorporating our topics into those education levels. And I've got some information here about sort of the lack of what we see in our education and some of the ways in which people have been trying to fill those gaps. So in K through 12, there's been a created an app-based textbook called Totality, which focuses on solar eclipse. So there's some topics covered in that. There's also a textbook aimed at middle and high school levels called Solar Science, and a PDF textbook from SWPC called Solar Physics and Terrestrial Effects, all of which are available and are good materials. Of course, getting them to be taught in our schools is a completely different matter, and that's a big challenge. So I'm not going to address how we do that, but there are some materials that try to make up for that gap that exists. The other thing that I wanted to point out is the Space Weather Underground campaign, which started at UNH, has been expanded to University of Alaska Fairbanks, and you can see a couple of pictures there from the Space Weather Underground. That's an incredible program which really does inject space science curriculum into that K through 12 level and get students excited about space weather topics. So that's been really impactful. It's only one thing that I know of. I know there are maybe smaller initiatives going on, but it'd be great to have expansions of those exact types of things into that curriculum. For college education, there's just such a lack of, so a lot of students take astrophysics as a general education course, but almost all of the textbooks leave out anything about space weather entirely. They might talk a little bit about the sun, maybe a bit about the solar wind, and possibly the fact that Earth has a magnetic field. And that's it. There's nothing about the coupling, about the connections, and then about any of the impacts at all. So this is a problem. There are some more advanced textbooks available I've listed there. Those are not appropriate for a general education solar system or astro or one of those big undergraduate classes. Those are a little bit more advanced, a little bit more focused in topic. So what we really need is to incorporate space physics into those astrophysics textbooks, those astronomy textbooks. But that just hasn't happened yet. And I know there's reasons for that. It takes time, it takes effort, it takes funding and all of that. But those are some gaps that we've identified within the formal education realm. Okay, so I will talk specifically about STEM students. This was more for, general education purposes. So the general public is sort of the next thing that we covered in the report. And this we identified as a big challenge, right, getting our word out to the general public. And we also said that university faculty and researchers are sort of this connection point between the public and the professional and the education part and the expertise, right? So university faculty, because they're usually part of their communities and they're integrated in their communities, and they also talk to students, which represent a huge part of the communities in which they're in. This is sort of that connection point, although places like Haystack, for example, have a huge role to play because they've intentionally tried to do so, but often it falls to the university faculty and researchers. Those include things like public demonstration nights, public night sky observing nights, classroom visits, event-specific outreach such as the solar eclipses and space weather events, when we see aurora and people get interviewed for the newspapers, for example. All those are examples of how researchers can talk to the general public and get that message to them. We also have been seeing an increase in so-called STEAM initiatives, which can be super powerful. And I know some of the people in this room who are involved in outreach have been kind of going this route, but STEAM is STEM plus art together. And it can just bring in people that normally kind of glaze over when they hear about science, or they decide like they're just not a science person. Maybe they say, I'm not a math person, and they walk the other way. But the STEAM initiatives can put the science into writing or music or dance or art and really get the buy-in from the whole public and get some of that messaging in there in a way that they want to listen to it and they want to attend and pay attention. So I really like those STEAM initiatives. That's something that's becoming more and more popular. Our finding for this section was that excitement is invaluable for outreach, right? We think of things like the Apollo missions, the Voyager programs, but we need outreach efforts to be sustained and expanded to have a significant influence on the public. And of course, this has to do with funding, and it has to do with effort and time, and I'm not here to solve any of those problems, and those are problems, but just to say that it does require, sustained or maybe coordinated approaches rather than just, one person doing a classroom visit and another person doing a public outreach night. We need kind of more sustained messaging. All right, so STEM students is slightly easier, right? Because they're already kind of halfway on your side. They got one foot in the door. And so engaging STEM students, I think we can all agree, is the primary way in which we recruit and retain talent in our fields. So we had a lot of stuff to say about how to reach out to STEM students in general. We, of course, have lots of longstanding hallmark programs. Those include the REU program, NASA's Heliophysics Summer School, the Space Weather Summer School from NSF, the NASA Finest Fellowships. NSF has graduate research fellowships as well, and then the space grants that exist in many of our states and are coordinated through the state universities. So those are wonderful examples of pathways where we get people into the field. Those need to be continued or even expanded, of course. We also see that there's additional, instead of these institutionalized programs, we see kind of like these smaller summer schools that have come up, internships, research appointments, and workshops. These are organized by university PIs as well as government labs. So some examples are the LANL summer internships. I even know many students in this room are currently in a LANL summer internship, as well as the year-long National Astronomy Consortium program. And there's also these shorter, immersive experiential programs that I think can fill a gap for students who can't do an REU or can't do a full summer-long internship for a variety of reasons. There's these shorter programs. One example is the Edge of Space Academy that we do at Iowa, where you can get students in and give them a crash course in, for example, we do hardware and space flight programs for just a couple weeks. And that can often, just having that touchstone can change the course of their career and where they want to go with their education and with their job in the end. And if they don't get that exposure, they go do other things, right? They do earth science or they do, astronomy. Not that those are bad, but if we want to try to get students into heliophysics specifically, these are some of the ways in which we can do that. The Advancing Diversity Report, I'll just make a note, from National Academies in 2022, found that early and ongoing experiences with authentic research is key to retaining students generally, and underrepresented minority students specifically. So this is a way that we can reach into pools of students and individuals who've been kind of historically overlooked in the sciences and recruit those into our fields as well. But it really requires authentic research, right? It's not like surface level, let's look at a PDF and talk about space weather, but let's get you using data or building hardware or contributing to theory and simulations and actually working on a research program, which is part of all the things that I've listed above. All right, so we also talked about citizen science, and we're going to have a talk just in a few minutes from Mike that will be talking about the HARP Citizen Science Project a bit more. Aurorasaurus is another really good citizen science project that has been going for years now and has done a lot of amazing things. So professional societies as well as nonprofit STEM partners can really be instrumental in helping connect and engage those interested in and involved with citizen science to add pathways into the solar and space physics braided stream. And this is a term that we use to talk about the different ways in which people enter and exit the field of heliophysics or solar and space physics. So the citizen science is a really interesting sort of new thing that is still having implications rippling outward. We don't really know how impactful it will be, but it seems to be incredibly useful currently and probably will even continue to be more so in the future. We sometimes call this participatory science rather than citizen science because citizen might have a certain connotation, but I think overall, colloquially, it's still known as citizen science. And this refers to collaborative work between teams of scientists and teams of non-scientists. There was, of course, a huge success story with the discovery of Steve, right? The strong thermal emission velocity enhancement that was really identified by citizen scientists rather than professional scientists. And there was a great coming together of those two groups to do many papers that are still being published and observations that are still being reported, as well as other things now that are coming out from citizen scientists that have not previously been reported or observed by professional scientists. Another one, of course, is the HARP that Mike will talk about. And I wanted to mention this SMD Science Activation Program at NASA, which is still on the website. So maybe it still exists. I'm not really sure because these days you don't know. But there is this network on the NASA page there that talks about these kinds of initiatives, and it's sort of a starting point for, okay, I have an idea or I want to start a citizen science project. Where do I go? How do I do it? What funding is available? What are some previous projects that have been successful? So I like that we noted that that page was very, very important, and hopefully they could expand that, or we recommended that they expand that. I don't know what's going to happen in reality. But yeah, those are some of the things that have happened recently and places that we could go forward with citizen science. The community in general is really enthusiastic about participating in outreach activities, as all of your raised hands indicated a few minutes ago, but adequate funding mechanisms either do not exist or are not obvious. And so that was one of our big findings from the report, and I know that again, talking about funding right now, huge question marks and huge uncertainties, but I know that you all have the enthusiasm to do this. And so talking about like, how do we do it? How do we incorporate it into our current careers without requiring much funding or advocating for that funding to be there in the future will be super important. All right, so cultural and cohort groups. This is a whole kind of realm of outreach that has specific programs associated with it and has had some amazing success that has come along with it. So cultural groups and institutions that have been historically marginalized in STEM represent sort of this untapped resource for recruitment into our fields, right? Because people aren't necessarily going in there and seeing them as a talent pool, those institutions, but if you do, there can be a lot of benefit to our fields for doing that. And I wanted to point out SOARS, which is the logo on the bottom there, which is the NSF Significant Opportunities in Atmospheric Research and Science program. It is managed by UCAR. It is a bridge-style program where SOARS, the program mentors students who identify as historically marginalized in science in the undergraduate to graduate school transition phase, and give them research opportunities. Over 90% of SOARS participants continue to graduate school, which is an amazing statistic to have in any program where you're talking about transitioning from undergrad to grad programs. So this is one example of a cohort group that has been hugely successful in getting students into our career pathways. Just to bring up Aurora Source again, they have done a lot of things for cultural groups and reaching out to cultural groups. So they have prioritized learning from traditional knowledge, culturally appropriate education that they produce, and integrating indigenous perspectives into their materials. So going throughout the First Nations groups and in US and Canada in the higher latitudes, and sort of incorporating their knowledge into the curriculum rather than just like going and forcing the Western US science perspective onto them has been really, really important because they're getting a lot of like buy-in and collaboration from the communities, which are, honestly have the right to be very suspicious about Western ideas coming in and saying like, oh, we want to teach you something. But instead of let's work together and let's talk about our common shared knowledge has been a much more useful approach, and we're seeing people getting into those career pathways and education pathways as a result. And then I just want to point out the International Polar Year that's coming up in a few years. So in preparation for IPY5, science organizations are highlighting the impact on indigenous communities. And of course, geospace science can have a huge role in IPY5, and it can represent huge opportunities for us. So thinking about how our science actually affects indigenous communities, or people at high latitudes, which include those indigenous communities, that can be really effective both to getting ourselves into the IPY5 framework, but also in general just doing that outreach so we can get more people coming into our fields. All right, and then recruiting from other career paths. So we have expanded sort of the definition of who comes into our field. We are now sort of including not just engineers and computer scientists, but management personnel and others who support and enable the science and space weather on the application side as well. So this is a little bit different, that has changed in recent years. And so we had some thoughts about recruiting from other career paths. We are expanding into new areas. We are looking at things like comparative studies of stars and planetary systems and other areas that require sort of a broader range of expertise than we usually think of for heliophysics. And so we have new needs that include computer and data science, artificial intelligence, machine learning, big data, software development, and industry-specific engineering. So the idea is to advertise to and recruit from related disciplines, not just from the astrophysics into space science fields, but computer science and data science, things that are more on the outside of our fields, but that we will need, especially going forward with more and more data. And I'll just end here with solar and space physics research benefits from an emphasis on interdisciplinary teams with overlapping expertise. So reaching out to those different career paths and bringing them into our field can be super beneficial in the long term. I'm going to stop there and ask if there's any questions in my last couple of minutes here. Thank you very much.
Thank you, Alison. And I would just echo what Alison said, that some of this outreach stuff can be incredibly rewarding when you see students come in and be excited about having a chance to do some research or to see some of what we're doing. It's helpful to us, and it's really rewarding as well. I think we have a question up the back there, maybe? Yeah.
There we go. Yeah, I was out there in DC with you. We worked very hard. I think that one of the things that struck me was the spread of knowledge among the folks we talked to in the various offices, from absolutely completely familiar with this to not familiar at all and really shocked. Even people on the space subcommittees that didn't really know what was going on. And we've had a lot of discussions about how to address outreach and increasing the knowledge of this. And you talked about astrophysics and earth sciences and planetary. I mean, that's cool stuff, great pictures, things can relate to. Our stuff is a lot more hard to relate to. We don't have really great, pretty pictures and things like that. I always talk about the squiggly lines. I mean, obviously Aurora is and so I have found, and we've had these discussions with people about, how do we address it? And talking about the science is not going to get the general public interested.
Right.
We need to talk about how it impacts them. Talk about how GPS impacts them, about talking about the Venetian probe that we had no idea where it was going to come in because they don't need satellite drag. And I think it's really important. You think about the audience that you're talking to, and the vast majority of that audience just has no knowledge and is completely ignorant. And being able to approach them from a status where they understand how it impacts them directly is really, really, really important.
Yeah, I agree with you. Let me push back on one of your points. There were no pictures of a black hole until just a handful of years ago, yet everyone knew what they were, right? So it's not just that we don't have pictures of our stuff, like we don't have pictures of reconnection. There's ways in which you can communicate to people involving analogies and cartoons and interesting diagrams that aren't just pictures of a phenomenon. And we haven't done an amazing job of that. We can do better, and there are people in this room who are coming up with that kind of material to do that better. And I agree with you about having an impact on people's lives and talking about that as an entry point. But other people are actually interested in discovery science, right? They know there's applications for this stuff, but they're actually interested in like what new things are there in the solar system to discover, and there's a lot. So we can kind of go in both directions, right? There's the applied space weather, how does it impact your life, but also what amazing discoveries are we yet to find that are out there waiting for us in our field of heliophysics?
I think we have time for one more really quick question. I think there's a question over there.
Oh.
Yeah.
Am I competing with someone? Okay, I'm just going to be quick. Alison, thank you. I really agree that outreach is something that we really need to get our words out and then share the excitement. So when we all worked on a decadal, the world was a bit different. And then what do you feel urgent, like in the coming months, not years, that we need to focus on in the area of outreach?
Yeah, so in the coming months, we need to focus on our elected officials. And on Friday, there will be an advocacy town hall at lunchtime talking about how we can communicate to our legislators in the short term to try to maybe have an impact on what's going on in our country right now. And yes, we need to focus on that first before we go into these years-long efforts of rewriting textbooks and things like that. So that's my answer.
I think we need to move on, but do you know Mike Hartinger? Are you able to say
Yeah, he's coming up.
So the final talk for today is another outreach talk. I think it's titled From Space Sounds to Penguins. The talk will be given by Mike Hartinger.
So thank you very much to the organizers for letting me speak here today. And thanks all for being here and listening. So I'm going to talk about some of my experiences with public outreach and engagement, going from space sounds to penguins. So I'm going to talk about two fairly different but related topics. And I just want to start off by acknowledging the many people, many great communicators that helped me put this talk together, as well as support from NASA and the National Science Foundation for several of the projects I'm going to mention. And the picture you're seeing there, by the way, is an Adelie penguin near McMurdo Station in front of the 2021 Antarctic total solar eclipse. If there's time, I'll talk a bit about the outreach related to that event, but it's doing what's called an ecstatic vocalization. So who doesn't get excited about solar eclipses? And apparently penguins do too. I was asked to talk a little bit about my journey into public outreach. And in the interest of time, I'm not going to go into too many details on all these projects, but the one thing I wanted to mention is that I definitely didn't start out thinking of myself as someone who would do public outreach routinely. I was very fortunate to have a lot of opportunities working with great communicators who mentored me and helped me along the way. And I think anyone in this audience can be successful doing public outreach. It doesn't matter if you have no experience. Learn from the great communicators in our field. We've heard from some of them already today. And we'll hear from many more this week. And there's so many ways you can learn about social media, how you can get involved in museums, libraries, and I'll talk a little bit about some of that today. But I think the one bullet point I want to mention on here, I was very lucky when I was a grad student. There was a program back then called the GK12 program, and Mark Moldwin, who was at UCLA, encouraged me to get involved in that program. And I was able to partner with teachers in high school, in a public high school in Los Angeles, and co-create and co-teach with them. And that really helped me challenge myself to talk to an audience who some of which was excited about science, but some of which wasn't. And so for me, that kind of formed my experiences moving forward, and also got me very excited about public outreach. And we already heard from Allison and Phil about the rewarding experiences you can have there, and I definitely echo that. It's something that does energize me as well. So I'm going to start with the conclusion slide, which is lessons learned, and actually a lot of what we just heard in the last talk with Allison and the Q&A really talks about this. But my lessons learned and the things that I hear echoed from other communicators who are much more knowledgeable about communication than I am are knowing your audience, connecting the dots from science to impact on people's lives. And that means more for us than just space weather. I'll get into that a little later. And also learning from other science communicators and leveraging resources and networks who are of good communicators. And the first bullet point I'll just mention, I mean, it might seem like a short statement, but there are volumes contained in those 3 words about knowing your audience. There's so much behind that, from the technology or the ways you're interacting with the audience to the audience that you're talking to. Are you talking to a 4th grader, or are you talking to a congressional representative? You really have to target your message to the different audiences. And I'll just walk through a couple examples in the talk today. So I'm going to start off with some discussion of space sounds and how I've been involved in some projects with them on the outreach and engagement side. I also just want to mention, when I say outreach, that can include things like one-way interactions, like lectures. When I say engagement, I mean more like collaborative partnerships and two-way interactions. But there can be many different types of outreach and engagement. There's not a sharp divide between those, and the definitions of those things will vary depending on who you talk to. But that's what I mean when I say outreach and engagement. So. What I want to talk about in the context of space sounds is you can have both outreach and engagement. And this diagram here is from the UN Office of Outer Space Affairs Space for Persons with Disabilities Special Report on Sonification. And it really drives home the fact that you have projects, all the words on that diagram are projects using sound to engage with the public or do outreach or do research, and there's not a sharp divide between them. So a lot of times when you hear about citizen science or participatory science, it's going to straddle a lot of these different areas. And like Allison just mentioned, it can also straddle into art. It can also straddle into art, and you have projects that will basically be working with musicians, for example, in sound. And I'll talk a little bit about that in the context of some of the projects I've been involved with. But the great thing is you can do all these things at once, potentially, with projects that involve space sound. And it's a great way to get people excited in the public. And our field basically has used sound for a long time. The words that we use to describe different types of plasma waves, Whistler waves, Hiss waves, chorus waves, these all came from the sounds that people heard when they were listening to measurements from a speaker. And you see this across the space sciences. Other fields have started using sound more, but our field really was doing it from the beginning. I think we've used it, and we still use it. Phil mentioned the ham site project. Ham radio operators use audio all the time, and it's something that's just ingrained in everything they do. The projects I'm going to be talking about involve ultra-low frequency waves. I'm not going to go too much into the science, but really the only thing you need to know about this is that these waves have these different wave modes in the nearest space have analogies to musical instruments. And we really push that hard in the projects I'm going to talk about. And what we push about this in terms of in the research side is that you can use automated algorithms to identify the different musical instruments or the different wave modes. But our challenge is the interactions between those wave modes and the dynamic, what we call a cacophony, the dynamic superposition of these different wave modes during something like a geomagnetic storm. This is really frontier science for us, trying to understand these modes that can occur during storms where you have different waves coming and going and playing together and interacting with wave-wave interactions. And that's something that audio can really help you with. And when you're working with volunteers, they're going to pick out patterns in the audio that you might not have ever found before with an automatic algorithm or with visual inspection. So how did this get started? Working with a colleague in the UK, Martin Archer, who was then at Queen Mary University in London. He was part of an effort there that was a broader effort in that university to work closely with high schools in the London area, doing various different ways of incorporating science into their curriculum, incorporating like actively doing experiments and scientific research into the high school curriculum. So he had a project called Magnetospheric Undulations Sonified, incorporating citizen scientists, or MUSICs. That project was basically meant to turn or audify a one-to-one mapping of data samples into audio samples. So he audified NOAA GOES satellite magnetometer measurements, and then he gave the students the resources to study the GOES magnetometer measurements and using sound and visual analysis, and also gave them the background in their high school curricula on geospace research to kind of formulate their own projects. And the wonderful thing that came out of this is as these students were listening to this GOES magnetometer data, they picked out a pattern that was complicated, but it was repeatable. They heard over the course of 1 year's worth of GOES magnetometer measurements, on the order of 10 or more of these events that I'll talk about in the next slide. And those form the foundation of a publication. Oops, sorry about that. Those formed a publication that was in Space Weather in 2018 and led directly to the HARP project, which I'll talk about. So I'm going to play you on the next slide, and you're going to hear there's audio of the audio that they heard. But this is going to be from a press release related to that space weather article. And you're going to hear about 1 week's worth of GOES magnetometer measurements. The GOES satellite is geostationary, so it moves through the same local time region once per day. You're going to hear 7 days worth of data, and basically it's a geomagnetic storm. The first, you're going to hear a burst of white noise when the shock hits. And then you're going to hear this monochromatic wave, this descending tone every day as GOES passes through the same region, and it goes down, the frequency goes down as it progresses during the storm. And this type of wave, this monochromatic poloidal mode wave, was thought to be very rare. This persistent poloidal mode wave was thought to be very rare. And they heard about 10 of these events just in 1 year of data. And it's something you can hear very quickly in the audio, as I'll play right here. So I'm going to move forward in the interest of time. But that's basically the pattern. And if you listen to a year's worth of data, you can go through a year's worth of data based on the way they codified the GOES magnetometer measurements in about 6 minutes. So you go through that data really fast, and you just hear those events coming again and again and again during the year they listened to. And so that allowed us to statistically look at that wave mode, or that mode of wave modes, I guess, that persistent wave mode, and write up a publication on it. So then we had a great opportunity. Right after that project, NASA started to fund more citizen science projects, and they had this great program called the Citizen Science Seed Funding Program, led by, shepherded in large part by Liz McDonald and others at NASA, who got really spun up the citizen science for heliophysics. And it was wonderful to have access to this program. It basically enabled us to develop an open source audio software, an audio processing protocol, and a graphical user interface. And that was what we wanted to do, was to take that success from Musics and translate it into a fully online audience. And so that's what we really did as part of the HARP project, which launched in April 2023. And I'll show you here. Oh, I guess it's going to play right away. Let me go back. So what I'm going to show you is just a walkthrough that's on our website for what you do when you interact with the HARP graphical user interface. And basically, the crux of this is that they're listening to about 3 days worth of, in this case, Themis satellite magnetometer measurements, and they have visual and audio cues to help them pick out different wave modes. And we don't just throw them to the wolves, we give them some training, and I'll talk about that in a minute, but I'll just walk this through so you can see kind of how it works. So here you draw a picture on the spectrogram, and you're using the audio. You can zoom in and zoom out in terms of the spectrogram. But basically the crux of it is they record a wave event, they box it, and they record some extra information about the event that we can then aggregate later and analyze, statistically analyze the different wave modes that are being identified. And what you heard there basically was we use the magnetic harp analogy. I guess I can't find this, but basically you can see the harp analogy on the top left there. And basically, these wave modes are like waves on a string. So as the satellite is moving away from the Earth, you hear a descending tone. As it moves back towards the Earth, you're running up the harp again, you hear an ascending tone. And that's kind of the crux of what we give them in the tutorial material. But we also, very importantly, ask them to explore the data themselves and identify unusual events or things that don't follow the trend. And that turned out to be very important as I get into some of the results from the HARP project. But before I do that, I want to get into kind of like how the sausage got made with HARP and talking more about those bullet points I talked about earlier. So knowing your audience, this is something that really we were helped by from people on the HARP team, but also from the NASA Citizen Science program that helped us to understand what we needed to do before we launched the project in terms of knowing our audience. And that means beta testing, basically. So we worked with small groups, high school students as part of a teen library program, and also students and researchers at UCLA, and also some people from the general public, people who are interested in audio in general, not just for science. And we did a public survey to determine the best audio processing. There's many different ways you can audify measurements, many different techniques, and we gave people a couple of different choices and asked them, when we knew there was an event, could they pick that out in the data? What audio processing allowed them to pick that data out the best? And so we incorporated all of that into the final product that went on our website, all of the feedback that we got there. And then connecting the dots from science to impact on people's lives. So again, the conversation that was in the last talk from Allison's talk was great, and it's something that we tried to do in this project as well. And that meant leveraging resources from NOAA and NASA, and also from past projects like MUSICS, when we put our website and our FAQ together and our tutorial material to explain why these waves are important. What can they do as far as affecting the near space environment, and how does that affect things like radiation in the near space? How does that affect geomically induced currents and power grids and so on? But that also meant, connecting the dots also meant we had musicians contacting us who wanted to use some space sounds in their musical compositions. So we provided, open source audio processing software that we put together in Python for them. And so those are the kind of examples. It doesn't always have to be about space weather. It can be other things as well that people are just interested in space sounds in general and want to incorporate it into their musical compositions. And then finally, leveraging networks and experience. So basically, I worked with a fantastic group of communicators in this who know way more about communication than I do, who have huge backgrounds in everything from being, some of these people were radio DJs, 2 of them actually were former radio DJs, Martin Archer and Alessandra Pacini. Annie Holland and Jamie Harold are experts on informal learning environments and museums and libraries and so forth. And that's just 2 examples. I mean, there are many, many amazing communicators. And we leveraged that as part of this project and just leveraged also resources available to us from NASA and the Citizen Science program at NASA. So just a quick rapid fire to make sure I get to the poor stuff. One of the things we tried to build into HARP was an ability to assess how engaged the people were who were interacting with our user interface. And we had just some rough numbers. We had about 1,800, actually 1,900 almost users on every continent except Antarctica. And this, I think the key thing in this chart, the bar chart here, is just that there's a fall off for sure. After about 10 marks, people tend to start getting less engaged. So most of our volunteers are in the 10 and less event identifications. But then it gets really shallow. The drop off after that gets really shallow. You have hundreds of people making more than 10 marks. And if you go all the way to the tails, we had about 5 or 6 people that made thousands of marks. And to put that into context, to make those marks and record all that information, this is like a full week's worth of work at least. So there are people that are just for fun, helping us out with this to do great science, providing us a labeled data set, and they're really enjoying it. And we're just starting to get to know our volunteers through the process of writing up some of the results. In terms of some output from HARP on the outreach side, we had some great collaborations with museums and musicians. A lot of this was led by Robert Alexander, who was on the HARP team. He worked with the Arctic House Museum, which has different, in DC, New York, and I think Chicago too, they have facilities where they do kind of interactive exhibits. So some of the HARP audio was incorporated into some things like the picture there on the left. He also worked on Golden Hour Remix, which is kind of fun. If anyone's interested, I could talk more about that. But then there were also some great related projects that leveraged some of the resources from HARP. Christina Collins, I've learned so much from her. She's working with the HAMSci project and has been a great interface between HARP and HAMSci, and we've started to talk more about future ways on how we can leverage each other's resources and knowledge on audio processing. And there's some follow-on projects that she's doing with open space, for example. And Lauren Blum, I'm going to talk about a project that she's leading in a couple slides. So as far as the science, what are we getting out of HARP and the early results that we're writing up now for a Frontiers special issue? I think the really cool thing, the first thing that I point to about this is when you talk about our magnetic HARP with these ULF waves, usually the frequency decreases as you move away from the Earth in general, especially in the outer magnetosphere. And then if you're a probe moving back towards the Earth, it'll increase. And that's what you hear in this classic example on the left. I'm going to just one orbit, play it right now. So it goes down and up. And then there's these other weird events where it doesn't do that, where you're moving away from the Earth and the pitch is either constant or it actually increases, which is pretty strange. And this is a big puzzle for us. We're just starting to look at the words that they use to describe some of these, and I'm not going to have time to go into that, but this is some of the qualitative information, but it's really cool to hear how they're describing these sounds. But I think, whoops, one more. There we go. But as far as the quantitative side, this is a really cool thing that I think has surprised me a lot as a ULF wave researcher. If you look at the 4 bars on the left of this diagram, that's the classic HARP. That's when the frequency decreases as you go away from the Earth and increases as you go towards the Earth. If you look at the 4 bars on the right, that's the opposite scenario, which is really strange. For me, the surprising thing was that, I mean, yes, there are fewer of these events, but there's a lot of them. There's hundreds of these events that they're picking out. And we're really trying to now dive into like what's causing these waves. Is it plasmaspheric plumes? Is there some other strange thing going on in the low latitude boundary layer? And so this is one of the first things that I point to that we're trying to write up now. But we're also going to release our whole data set and hopefully have lots of follow-on studies on this, what's turning out to be a very rich data set. Okay, so I wanted to plug real quick Lauren Blum's follow-on project. She's leading an NSF Eager project, doing the same thing with slightly higher frequency electromagnetic ion cyclotron waves, and really getting into the audio processing to pick out these waves in NOAA and NASA data sets. This is going to be I'll just play a quick clip of some of the early audio processing they're using on the NOAA GOES satellite. So some of what you're hearing there is actually an artifact in the GOES magnetometer data, but the little chirps that you heard were these EMIC waves. And they're trying to pick out events that are challenging to identify with automated algorithms. And if there's time, I can talk more about that later. But I also wanted to plug Tiffany Costello, who's working with Lauren Blum. And she's doing a great aspect of this in terms of the outreach side. She's doing the audio processing, but she's also talking about the audio processing in a series of Instagram posts or YouTube posts. And you can see more about her videos. There's going to be more coming soon because we just got started. But she's basically plugging both the audio processing for people who are interested in that side of things, like musicians and so on, but also the science. So this is a great way. And I just wanted to mention that social media is something I know very, very little about, but there are amazing, amazing communicators in our field, like Tiffany, and also like Vince Lavina, who's done a ton with social media to really amplify the message of why this research matters, why our research matters. Okay, I know we're going to talk about burnout later this week, and I wanted to do 2 things on this side. I wanted to plug a really excellent recent review paper that just came out by Grandin et al. 2025 on citizen science as a whole. But I wanted to just point to one thing they mentioned here about, you have to, when you're doing these kinds of projects for citizen science or for public outreach in general, you have to be aware of your work-life balance. I mean, for me, you can get hundreds of emails sometimes from volunteers all coming in at once. And there are strategies for dealing with that, to do that communication. But I think the overarching thing is like, use outreach. I mean, I like to use outreach, like Allison said, to get energized and really enjoy what I'm doing and communicating the science. But you also have to be mindful, if you're over-volunteering, if you're spending all of your time on this stuff, try to pick like 1 or 2 things and focus on them, and just be mindful of how much time you're putting into this. If you're spending your whole weekends on this stuff, some of us might enjoy that, but if it becomes a chore, it's not something to do. And I just encourage you to read this review paper. It has a really great perspective. And also, of course, we're going to hear more later this week about this. Okay, my last couple really quick minutes, because I don't have time for questions. Allison mentioned the International Poor Year. If there's not enough time to talk about it in depth right now, I just wanted to mention that there's going to be there's probably going to be multiple discussions on it this week, but I know of one at least on Thursday at 10 a.m. in room 309 for the GIC GMAG session. If you want to hear updates about what International Poor Years are and how you can get involved, feel free to come to that. The QR code here takes you to a National Academies report from the last International Poor Year in 2007, which had a whole chapter devoted to outreach. And they had this great message: what happens at the polls affects us all. And I think our field really can easily convey that message. The last IPY, there wasn't as much engagement from our community in that one. I think part of that was because we had our own International Heliophysical Year happening in parallel at the same time. And also it was a solar minimum. But in 2032, when we're going to have IPY5, it's solar maximum, and there's a total solar eclipse in Alaska in 2033. So this is, as we know, eclipses are huge opportunities to get people interested in geospace and space weather research. And of course, like Alice mentioned, space weather events. We actually have pictures of the aurora moving equatorward, and you can overlay them on areas where we lost precision agriculture. People right here in Iowa couldn't use their tractors during that the Gannon storm in 2024. So it's really a great opportunity to communicate our science to the rest of the general public. And I know I don't have time to talk about this really, but there was a recent National Academies meeting on early plans for IPY5, and the only reason I'm throwing this slide up is because there were a couple of really great talks on at that meeting, where it really is an example of how we can learn from other science communities and how they can potentially learn from us. But I really liked Richard Alley's keynote lecture there. he really connected the dots that, for 3 cities alone, to harden them against sea level rise was $230 billion. And he quantifies where that number comes from. To monitor ice sheets, which are a huge aspect of reducing the uncertainty in sea level rise, is a tiny fraction of that cost. And that's just 3 cities. We're talking about we need to worry about the whole world, when we're talking about sea level rise. So it's a tiny fraction of what you need. Your investment pays off multiple times in terms of like environmental monitoring in the poles. And the same is true for us. We can make that case. We can talk about the economic impacts. And we can also talk about how people that we train go on to other fields potentially. And so it's not just about training more scientists, but the skills translate to other fields. So just check out Richard Howey's talk if you have time. And then, of course, I know I'm probably a broken record, like everyone's talking about this right now, but it's a big topic right now that we're all dealing with. I think the budget cuts to NASA and National Science Foundation could be really disastrous for our ability to do these outreach and engagement programs. What if we no longer have the citizen science program at NASA? So now is the time, like Allison said, now is the time to talk to our congressional representatives. And the QR code takes you to the Heliophysics Coalition message that went out a couple weeks ago. And I just want to say, this is another type of outreach, another type of communications where knowing your audience and connecting the dots is super important. And you don't have to do it alone. You can leverage resources. And with that, I think I will just leave up my summary slide and thank you for your time and take any questions.
Thank you. That was really fun. And we're so used to thinking of our science visually, but our brains have evolved to process audio in different ways, and it's like a whole new window into what we can, how we can understand things. So I think that was really exciting, and thank you for that. I think we have time for one really quick question, if there is one. Oh, there's a question over here. Mm-hmm.
Thank you for that great talk, Mike. I have a question about, in your experience, what connects more to young people and to people who make decisions? There is the field of astronomy has really positioned themselves as curiosity-driven science. And we are somewhere in between. We often position ourselves as security guards of space environment. And I don't know how exciting that would be for young people, but for people who make decisions, that is something that is important. So in your experience, what has connected more with people, the curiosity or this application? Thank you.
That's a great question. And I think I don't have a simple answer because I think it really depends on the audience. Definitely congressional representatives, a lot of them will be interested in the economic impacts and the infrastructure industry. But I think, for example, when I've talked to high school students, both of those messages can resonate. There are some that really engage with the discovery science, and there are some that I would say actually are really concerned about like how they can make a difference in terms of like protecting society and hardening our infrastructure. There are actually high school students that get passionate about that too. So it's kind of I think it's both actually. But I think as you go to younger and younger ages, it definitely varies, and I don't have a simple answer there. But it's been interesting to see for me how both of those messages can potentially resonate, even for the younger crowds.
Well, thanks again, Mike. I think we do have to move on. So we have 2 more presentations, both of which are short memorial talks to recognise leaders in our field that we've lost recently. The first talk is to remember Catherine McWilliams, and I think it's Dan Billett is going to be. Is Dan here? Oh, yeah. Mm-hmm.
Yeah, thanks. I wish I was here under better circumstances, but this year we lost one of the most influential Canadian physicists in our field, Professor Catherine McWilliams, who was PI of Superdan Canada and also chair of the International Superdan Consortium, passed away this January after a very short battle with cancer. Catherine was tirelessly dedicated to everyone she worked with. And if you knew her, which I think many people in this room do, or knew her, you'll understand that Catherine wasn't the kind of PI that you just add to a paper out of an obligation and expect to hear nothing from them. Catherine was the kind of person to take your paper and return it with so much red ink that you then couldn't see the paper that you originally sent to her. But then you didn't mind that because she'd have pulled out some obscure reference from 20 years ago, which then ended up fitting the research perfectly. So she was just a great collaborator to work with. Catherine McWilliams was Supernon, and Supernon was her. She literally built it from the beginning. The bottom right picture on these slides, that's from the original build of the Saskatoon radar in 1992, when Catherine was a summer student. So she was literally there from the beginning. And her memory will echo there for years to come, and that's represented by a handprint, which is cast in one of the antenna tower's concrete bases. That's also there in the bottom left. After Catherine finished her master's at the University of Saskatchewan, she went on to do a PhD at the University of Leicester in the UK. That was on a prestigious Commonwealth scholarship. And then she came back to USask as a postdoc in 2002 and became a professor in 2004. At USask, Catherine became the very first female tenured faculty member in physics. And then skipping ahead, in 2022, she became the first Canadian ever to be recognized as an honorary fellow of the Royal Astronomical Society. Catherine, more kind of personally, Catherine saved Supernon Canada basically from the brink of turning the lights off by securing us as a Canadian national research facility. And not only did she manage to build an additional 2 new radars, she built the largest team of engineers of any Supernon group and kickstarted many, many careers that way. Her enthusiasm for this field, her radars, her colleagues, her students, and her engineers was boundless and inspirational. And the way she spoke with those not in our field was passionate and loving. Catherine gave many interviews, and she gave a lot of them. She would say that our lab is the biggest one in the solar system. She was really good at just communicating. And to those in our field, she would lift them very high above herself. There are many examples, but one I'll mention is the Canada-Norway rocket launch program, which she led over the years, and that funded over 250 Canadian students. She was a true leader and incredible human being, and many of us will remember her for the sincere generosity she gave in every aspect of her life. And we should all strive to be more like Catherine in both our careers and our personal lives. I'm incredibly privileged to have known Catherine and to have been a postdoc for the last 6 years. She built me and many, many others up to love this field, and her absence now at the University of Saskatchewan within the Supernon, CEDAR and GEM communities, as well as for her family, has been and will continue to be extremely painful for all of us. So just finishing, I'd just like you to please join me in paying respects and love for just what has been an incredible titan of our field. Rest in peace, Catherine.
Thanks, Dan, for that tribute. And we have one more. I think Julio Urbina will speak for John Matthews, who also passed recently.
Okay, hello everyone. My name is Julio Urbina and I am a professor at Penn State. John Matthews was, how do I go back? Oops. Okay. So Professor Matthews was a mentor to me, on a personal level. It was shocking for me to learn that he died when he was traveling. He was in Spain in October of last year. It was shocking because I used to meet with him every week, and the week he was expected to return was the next day after the election. And we were supposed to have a meeting about research, and he didn't show up. I thought he was very upset about the election, and he just didn't want to do anything. But called him, texted him, and went to his house, and didn't see much. Finally, reached out to his children, and I learned that he died of a heart attack when he was in Spain with his partner. And what I'm trying to do today, just as John liked to do things, he liked to keep things very simple. So I'm going to try to highlight his accomplishments and perhaps, if I have time, share a couple of stories about him. So John did, he has a long-time research contributions to CEDAR, AGU, URSI, and so on. He did a lot of work in ISR, also in meteors. And one of the topics I was working with him was meteors, fragmentation, differential dilation, and a number of things that we wanted to explore. And we're also working on GPS and other things that we wanted to understand. He did a lot of pioneer work with Arecibo. He was a long-time user of Arecibo, and also Jicamarca. We were devastated when Arecibo collapsed, and we worked very hard, actively trying to bring back Arecibo, and we will continue to do so. I hope our community helps us in that direction. He did a lot of work with the D region and the E region of the ionosphere. Make a lot of contributions on tide, winds, sporadic layers. I still remember that he has a review paper from 1998 on sporadic layers, and I keep always teasing John that that paper is very old and he needs to write a review because I used that paper for my thesis, for my PhD thesis, right? So he was very excited about that, and we were going to do that together. But anyway, and a lot of work on micrometers with Jicamarca, with Arecibo, understanding the impact of the atmosphere on our daily life. And of course, he was an amazing person to me. He was a mentor. When I told John this, that when I first met him, when I was a graduate student, I was terrified about him. He looks very serious and very professional. But when I joined Penn State, I got to know him at all levels, and that scaredness for me was nothing. He was a down-to-earth person, willing to share his knowledge, willing to share everything, willing to teach you everything, and he wouldn't mind if you yell at him about science, right? If you are wrong, that's what you should do, he would tell me. Shut out. Just fight for what you think and just prove to me your ideas, right? He also started writing stories, many stories about his childhood and science fiction stories. I hope with his family we can publish some of those. And we also had, a lot of lunch, deep philosophical discussions that we usually don't have anymore at universities, but with John, we used to read books, many books, about life, about, why are we here, what are we going to do, and what is science, and what is amazing about our field, and how we can do more about reaching out to all kinds of communities, especially those communities that do not have opportunities, those communities, those students who never made it, right? So those, because John comes from those things, and so do I. So we're working very passionate about what we can do. And it was amazing for me to have these discussions with John. He was so inspirational. And as I said, he served in the NSF CEDAR steering committee. He was one member a long time ago. He also, at URSI and AGU. And I hope with his impact and contributions remain central to our work, and his papers continue to be used and referenced. And join me in honoring his memory, and I hope lasting influence about John Matthews. Thank you.
Thanks, Julio, for that heartfelt tribute there. And it's sad that we lose people, but anyway. So I think that concludes the sessions for this morning. Our theme has really been, the health and vitality and collaboration and community that we have here. Even our distinguished science lecture was really focused on how we work as a community and how we can work together. For those of you who are enthusiastic for some more traditional hard science talks, we've got plenty of those this afternoon in our breakout workshops, and there's plenty more to come this week. So join me once again in thanking our speakers for this morning. Enjoy your lunch break, and lots of science to come for the rest of the day. So thanks, everybody.